First off, there's going to be a piece of homework due tomorrow at midnight. It is a very quick assignment, which just ensures that you've installed Dr. Racket, and it is a test of the Marmoset automatic grading system. So this assignment will be automatically graded. I won't be looking at your submissions, and as soon as you submit it, you'll be able to tell what the score is, since almost instantly. Now, the way that Marmoset works, so these are some comments on Marmoset. Marmoset is a species of monkeys, and it's a testing service. So Marmoset has public tests and release tests. Now, you know the score of public tests, so your work will be tested by checking whether it behaves correctly on certain inputs. In this case, the assignment really won't have inputs. You'll just be defining some expressions, and I'll check whether those expressions are defined correctly. But each one of those checks is known as a test. And in order to get full points on the problem, you have to pass every single test. If you pass only a subset of them, you will get partial points for the tests which you pass. Now, when you submit it, the value of instant feedback is that you know right away whether you've done something wrong, and then you can retry. Now, in order to discourage just retrying and submitting very small iterations instead of testing it yourself or figuring out what is wrong, some of the tests are release tests, which means that you have to spend a token in order to see what your score on the release tests is. So does that make sense?
Yeah.
Now, the one thing that I need to clarify is that when you submit something, it will have all of the tests run on it. And even if you do not know your score on the release tests, they have been scored. So if you're out of release tokens and you submit something, it'll still count as a submission, although you won't know the results. Now, in this case, the homework will ask you to define 4 expressions, and their first one is covered by a public test. And the other 3 are covered by release tests. And you have 3 release tokens. And they regenerate once every 24 hours. So this homework, the third homework, which is called PG1, is due on Thursday at 11:59 p.m. And it's a rather quick assignment, but it'll quickly familiarize you with, well, typing things into Dr. Racket and using Marmoset's release and release token system. So that's the first comment. Any questions? Okay, so today's class, I'm going to do several sections. first we're going to continue working in Dr. Racket, and then we're going to move back over to the blackboard and write things. So I want to cover Racket in slightly greater detail. So first off, Racket program consists either of definitions or expressions, actually multiple of them. So we can say, for example, that a program is either it's a series of definitions or expressions. Zero or more of. And then a definition or expression is either a definition or expression. Now, expressions are things which get evaluated. So for example, 5 is an expression. Hash true is also an expression. And once you type in an expression, if it gives you an output, that output will be a value. It will output a value. Now, one thing that we saw last time is, for example, let's say I try and multiply 1 with true. Then I'll get a complaint. And the complaint is that multiplication expects a number as the second argument, but I was given true. Now, why is that an error? It's because true is not a number. And that's because values in Racket are classified. Values should be thought of as pieces of data. In a certain sense, the expression +2, 3, well, in one sense, that expression is data, but in another sense, we should not think of that as some finalized piece of data that you can push around. It's something that will eventually produce data, but at the moment, it's some sort of compound expression. But things which are values, Racket classifies them, and you can apply predicates to them, like number. So values in Racket form a universe. Well, Racket has a universe of values. And some of these values, for example, numbers, Booleans, strings. And each type of value has associated predicates. So for example, for these, they would just be number, question mark, Boolean, question mark, and string, question mark, and case matters. So what is a number is something that I'm not going to define. Racket has lots of different forms of numbers. For example, if I divide 1 by 2, if these were whole numbers and this were to produce a whole number, then the output would probably be 0. But even though both inputs are whole numbers, Racket will switch into the world of fractional numbers, or in this case, given as a decimal representation. But if I said a third, for example, which can't be represented as a terminating decimal, it would probably output a fraction. Except when it doesn't. Interesting.
I think this must be a bar there. Just probably can't see it since the screen is dark.
It looks like a decimal point, but what happens if we multiply it by 3? We'll get 1. Okay, so a third then is not 0.3. Oh, you're saying there's a bar over the 3? No, it doesn't look like it's.
A bar shown on my screen. When I do.
You see it on your screen?
Yeah,
oh, yes, I see. It's also on my screen as well. There is a very subtle bar there.
Yeah.
Okay, well, if we say 17 and let's say 7. And there's also a bar over some digits, so it's also presented as a repeating decimal. But if I multiply this by, for example, 7, then I'll get 17 again. So numbers are really something complicated. There's also a square root function. And what happens if I take the square root of -1? So numbers also include complex numbers. So there's a lot of internal implementation details that are hidden. And notice that if I form an irrational square root, like the square root of 2, it'll tell me that this is an inexact number. Whereas if I ask it to perform the square root of 4, it'll see that, oh, that square root can be exactly represented by an integer, so I won't form an inexact number. So there's a lot going on under the hood for numbers. It's much more complicated than that. But you can still classify them by number ? And whatever's outputted here will be a number value, although there are different types of number values. So sometimes it'll represent rational numbers with repeating decimal expansions, complex numbers, or inexact decimal numbers. And we can call these different types of values by certain names. We introduce, these names are not names in Racket. They are names that we're going to use for describing functions. We'll describe the types of values as, for example, number with a capital first letter, Boolean, string. So for example, an example of a number is 2. Of a value of type number. And then I can write it here. And if I press run, it'll evaluate that expression and just produce the value 2 because it's already a value. Now, other forms of values that I mentioned are, for example, we can have booleans, hash true. We can have strings, which are enclosed in double quotation marks. There are also characters. I think characters would be denoted like this, for example. With a backslash. So that's an example of a character. Okay. They're just called, they're shortened to characters. Char. So these are examples of values. And informally, we give names to the types of those values. So there is a universe of all numbers, a universe of all possible values that Racket will classify as a number, a universe of all possible values that Racket will classify as a Boolean. Well, that universe is small. So the universe of Boolean values, the universe of values of type bool, is just consists of only two values, true and false. So that's one level of classification that Racket has, and you can see this classification in action when you try and do things like multiply one with true. If these things weren't values in the system, but only bits on a computer, then perhaps multiplication would attempt to operate with some piece of data which is being interpreted incorrectly. But that's not what's happening in Racket. In Rackets, they'll intelligently, when you try and do something like multiplication, check whether what you're multiplying is two numbers. And if not, it'll throw an error saying that multiplication expects a number as a second argument or some value of type number in the way that I'll be describing it. So these are the most simple type of expression. All values are expressions. And now, for the simplest type of definition that we can have, is just defining some name. So now we're going to introduce a name into the language. So let's say Tom. That's some name. And we can bind Tom to any expression or any value. So perhaps true. Now, this definition here, when run, will introduce the name Tom into the language. It doesn't produce any value. This is not an expression. Definitions do not produce values. Definitions change the rules of the game. So if we type in, for example, Tom now, that's a name that refers to true. Any questions about that?
I have a question. So it says an example of a value of type number, and then listed below you have true,
Thanks.
hello. I thought they weren't numbers. I thought true
Good.
couldn't be a number. Oh, so
Yes.
they're separate.
Thanks. The important correction. So this is a Boolean. Of type Boolean, string, and char, character. Now, okay, we can, for example, say that let's define some names. And let's say that we're going to define names based on their rating from a 1 to 10 scale very arbitrarily. So we can say maybe Tom is 6 on a 1 to 10 scale of just the rating of a baby name. Maybe on how rare it is. Now, it turns out that Racket lets you define names that represents the full spectrum of names that sane people name their children, which isn't a feature that's available in other programming languages. And I think the joke can now be seen from a mile away. Does anyone know what the next name that I'm going to type is? So, okay, I think this would be a good way to type it. Sane baby names that people name their children.
Oh, come.
So this is the name that Grimes named her son with Elon Musk. Well, in California, they had to change the hyphenation. I know that's not an ASH, but names can support names support Unicode characters. It doesn't just have to be 256 ASCII characters. You can define Greek letters as well. And so you don't have to worry about, well, how to input every single possible character. But if you type in a LaTeX macro, for example, \alpha, and press, this is on OS X, Control, and \, that produces an alpha. Okay, so this is one form of definition. Definitions define names, but that tells us that there's also another thing that we have that's an expression apart from just these values, and those are names. So for example, names are expressions. Now I can type in a name that hasn't been defined yet, let's say my own. I'm doing everyone with lowercase. And then it'll say, this variable is not defined. So in particular, names are not values. Names need some evaluation. If I type in alpha, if alpha were a value, then that would be the sole output. But alpha is not a value. The meaning of a name is what it has been defined to be. Now, some names, for example, do come from context. We saw last time in the demonstration that if I just type in E, it'll give me the number 2.71. Some names are predefined. So for example, E, pi. And also names of functions like multiplication. That's something that's also defined. Now, I can define the names over, in which case only the most recent definition will apply. You should think of it as not I'm changing the definition, but I'm making another definition that has precedence because it's more recent than the former definition. So I can define, for example, E to be 3. This is fine. Oh, beginning student language will not let you do that. Good. So in beginning student language, you are not allowed to redefine names. It'll also complain. Good. Names can only be defined once, and you're not allowed to do something like define multiplication to be something. So if I tried to define multiplication as addition, I suppose that beginning student language would also complain. Very good. Now, then names as expressions are susceptible to rules. And so the rule governing how names behave with respect to evaluation is that a name goes to its definition, what it's defined as. Or in another way, suppose that we have, for example, define a certain name to be a certain value. Then, if you look at the statements, the expression name, the way that this will behave is that this program will get transferred into this program. Now, so for example, we can write this as a computational rule on how names behave. Names are not values, and the way that you evaluate a name is by looking up its definition. And if you try and look up the definition and the lookup fails, then you get an error saying that the name has not been defined. This name is not defined. In this language, they call it a variable. Any questions? Or does anyone want me to try something with these things?
Yeah.
Sorry, go ahead. Okay.
So can you have like a name evaluate
To what?
to another name, and would that like
Okay,
call it a
good.
custom?
Let's try that. So let's define. Aha, very good. So we have some definitions here. Okay, I'll leave them here. let's define, let's say name1. And let's define that to be, well, something. And you want to define name2. Now, I think so let's try this first. Let's say name1 it has value 1 and name2 has is name1. So that'll work. And if I say name2, it'll give 1. So what we see then is that names do not have to be defined to be values. So point 1, names don't have to be defined to be values. In general, the following is an expression: define, name, expression. Now, the way that Racket will behave is that before processing the definition, it'll evaluate the expression. So, for example, if expression eventually reduces to a value, then this definition will itself eventually reduce to being defined in terms of that value. Now, I believe the question that you were asking was not this. You wanted me to do something else. What did you want me to do?
Do it recursively.
Yeah. So let's define name4 in terms of name3 and name3 in terms of name4. So what happens then? It'll say name4 is used before its definition. So what we discover is that statements, in other words, definitions or expressions, so this type of thing, either a definition or an expression, are evaluated, well, you could say from top to bottom or from left to right, but they're evaluated sequentially. Well, not necessarily evaluated, or processed sequentially. Now, so when an expression is processed, it produces a value. And when a definition is evaluated, it changes the rules of the language. It introduces a new rule. So in other words, what happens here is that at the moment that you're trying to process this definition, there is no rule for evaluating name4. And in order for a definition to be processed, when you have define name expression, that expression for the definition to finish processing has to reduce to a value. Now, for example, if expression has undefined names, then no rules will apply and Racket will get stuck and produce an error. So for example, you can't make recursive definitions like this. Mutually. Any other questions? Okay, I'd like to show you something that I rather would not have shown you at this stage. But since the assignment is going to be due on Thursday, I'm certainly not going to not discuss it for 2 classes in a row. So let's say we make a definition. And let's say we define, let's say, x to be 2 plus 2. 2 plus 2 is not a value. And then we, for example, say x times x. Now look at the screen. At the top right of the screen, I have this button called step. When I press this button, magic will happen. And in particular, now at the top of the screen, you see this bar, stepper. When I go to the stepper, you'll see how it is that Racket processes the statements and applies the rules. So our original program, which you see here, has 2 things which are either a definition or an expression. Racket will process each definition and expression one by one. The first one is define x 2 plus 2. Now it'll look at 2 plus 2, and 2 plus 2 is not a value. So Racket will try and reduce 2 plus 2 down to a value. It'll perform the computation and it'll get 4. Now 4 is a value, and Racket will check that it's a value, and then it'll go from there. So then I press the button next, and I see what happens next. Now, Racket has checked that 4 is a value and that this definition is allowed to stand. Then it'll look at start processing the next expression, which is...
Taras?
Yep.
I can't see the stepper GUI.
Oh.
I just see the Racket thing, but not the stepper.
Do you see what I'm highlighting?
I mean just the plus 2, 2.
Oh, I see. That's okay. No, I see. The stepper is considered a different window. Okay, do you see now?
Yes, I do.
Thanks for letting me know. So I'll need to switch every single time, re-screen share every single time I want to use the stepper. So, okay, the programs are, oh, and I can't navigate back easily either. Well, the program has 2 statements. The first statement is define x, well, 2 plus 2. That's not an expression, it's a definition. In order for Racket to be done with the definition and introduce a new rule into the language, it needs to evaluate this right-hand side of the definition down to a value. So you'll see that the first step that Racket will do in processing this definition is calculate 2 plus 2 as 4, right?
Yeah.
Now 4 is the value, so Racket is happy with this definition. And so this definition will be allowed to stand. Then it'll start processing the next expression, which is the product of x and x. It'll start it can't multiply x and x yet because the name x is not a value. And so it'll try and reduce this x to a value. Now, there is a computation rule that applies to the name x. That rule is a lookup of its definition. Its definition stands immediately above it. Define x as 4. So the way that this first argument will get evaluated is that it will look up the name x and replace it with 4. Now, 4 is a value. So the next order of business is to bring the second operand down to a value. There is a computation rule that applies to x, its definition again. And so once again, x is rewritten as 4. And now that both of the arguments to the multiplication are number values, the multiplication will be able to, well, the multiplication will be performed and it'll compute 4 times 4 is 16. And that's how the program ends. The expression originally, product of x with x, will get reduced just to 16. So now if I close the stepper here, you'll stop seeing this. And now we're back to this window. So in fact, you can see Racket apply the rules one by one instead of just computing the values. So for example, if I pressed run right now, you see my screen again, right?
Yeah.
Then the definition does not produce any value because it's a definition. So definitions do not produce values when processed. Now, this is an expression. Will be evaluated and produce values. Are evaluated and produce values. If I just run the program, you see that the output is nothing for the definition, although the definition has now changed the rules of the language, and the expression produces a value 16. Now, I'm in an environment where I can still continue to interact with the program, even after it's been run, and this definition stands. So in the interactions window, I can type in x, and then I'll get 4. Or add x with 16, I get 20. So names are also expressions. That's one thing that we learned. Now, we have primitive functions or primitive operators. Multiplication, addition, subtraction. Well, multiplication, division, addition, subtraction. Or things like sign, or things like exp, or things like expt, which raises a number to a certain power, which I didn't have last time. And it looks like we can form expressions like these. These should also be expressions. So another type of expression is, and now I'll use any one of these names and I'll call any of one of these names a primitive operator. And then some number of values or some number of expressions. 0 or more. Now, in particular, none of these primitive operators accept 0 arguments. In beginning students at the moment, each of them would need at least 1. However, also in beginning students, the number of arguments that you provide is determined. So for example, if I try and add 3 numbers, it'll allow me to do it. So addition, but if I try and form an exponentiation with a different number of arguments than it expects, it'll argue, saying that it expects 2 arguments but found only 1. So when Racket tries to evaluate an expression as above, the number of arguments might mismatch the signature of the operator. This is a new term I'm introducing of the operator. Now, it looks like addition will accept any number of arguments. Will it accept 0? That's one thing. Will it accept only 1? No, addition expects at least 2 arguments. So, for example, addition expects 2 or more arguments. And if you try and evaluate addition with, for example, no arguments, or addition with only 1 argument, you'll get an error. Similarly, Rackets, these primitive operations apply to values of only a certain type. So for example, if you try and add 1 to a Boolean, you get an error saying that it expected a number, but you didn't supply it with a number. So such a thing is called a procedure call. Now, procedure calls are not values. Are expressions, but not values. So if it were the case that a procedure call were a value, then if I typed this in, what I would expect is just the same output as what I gave it. But that's not what happens, because it's not a value. There is some evaluation left to be done, and Racket performs that evaluation. Any questions? Okay, then next we have function definitions. So function definitions have this form. For example, let's say I want to define, I'm going to check that add is not a name in the language. It isn't. Good. So function definitions unlike definitions of names, enclose the thing which immediately follows the define in parentheses. And the first thing within the parentheses should be the name of the function. And the next thing, the things which follow are the names of the parameters of the function. Let's say I'll just define add of x and y to be the same as x plus y. Then if I type in add 1, 2, it'll compute 3. Now, what happens if, for example, I'm going to go back to the place where we looked at the stepper. Instead of defining add xy to be x plus y, I define it to be x plus 2 plus 3. So the value of y isn't going to be used. Or, sure. And I'll say add 1, 1. So what do people think the stepper will do when processing this definition? Will it reduce the 2 plus 3 to a 5 or not?
I would think so.
So let's try. It doesn't. So for example, this definition, function definitions, the definition just stands. The definition is already considered to have been processed. And then when I invoke the rule as add 1, 1, it'll take this definition, it'll take x and y in the definition, and it'll replace them with the arguments. Y doesn't occur, but this x will get replaced with 1. And then the sum of 2 and 3 will just sit here as it did before. Then, in order to evaluate this addition, before it can be evaluated, Racket needs to evaluate what 2 plus 3 is. It evaluates that to 5, then the 1 plus 5 goes down to 6. And that ends the computational trace. So what we learned here was that if you have a function definition, even if that function definition looks like it has expressions which can be reduced, function definitions are not reduced when they are processed. That's a stepper again. So let's write potentially reducible expressions in function definitions are not evaluated when the definition is processed. So for example, if I given, let's just say, let's call the function f of x is equal to x plus 2 plus 3, then f of 2 will get reduced to, in one step, the following. Then this in turn will get reduced to which will finally get reduced to 7. Any questions? Right. So what does it look like? How do function definitions behave? And in general, what's the general type? What is the general form of a function definition? Function definitions are definitions. And the general function definition looks like define, then the name of the function. Now, let's see if we can define functions with no parameters in beginning students. So let's say I just define the function f with no parameters, and it should output 2 all of the time. So in beginning student, but not in full Racket, function names should have at least one parameter. So you have the name of the function, the name of the first parameter, and then 0 or more other parameters. And the body of the function is just some expression. Because once you evaluate a function, it should produce some, well, once it's fully evaluated, it should produce some value. So the body should be an expression that will eventually get reduced to a value. Now, the computation rule then is that if you have some definition, let's say function name, and let's say the parameters are x1, x2 and x3, then if you have the following expression, and you supply it with 3 values, value 1, value 2, value 3, in one step, that gets reduced to expression, but with substitution of the variable names for the values. So x1 is replaced with v1, x2 replaced with v2, and x3 replaced with v3. And in general, you have such a computation rule for the number of parameters that your function is defined to have. It's impossible to define just as a syntax level user-defined function that accepts any number of parameters. But that functionality, as we'll see later, can be achieved by just passing a list of parameters. But don't worry about that for the moment. So there's another form of computation rules. When you take a name and you enclose it in parentheses, and you place some number of expressions here, what Racket will try and do, it'll interpret the name that begins this parenthesis enclosed expression. It'll interpret it as a function. It'll try and look up the definition of the function. Then if it's able to find this definition, it'll look at its body. It'll look at the parameters of the function. It'll try and see whether the values that you've passed to it, there are as many as there are parameters of the function. And then it'll take the expression, and in the body, it'll replace every occurrence of x1, x2, and x3 with v1, v2, and v3 respectively. And in one step, you'll have this reduction. So that's another form of computation rule. And this is very tricky to define. We'll do this next week or on Friday. So right now, I'm still telling you these things at a slightly high level. So far, what you've seen is that Racket has definitions and expressions. Two types of definitions that Racket has are either things that just define names, or things that define functions. Now, depending on which one of these two definitions you use, you'll get some computational rules introduced. Definitions introduce new rules of computation. Definitions of this form introduce the computation rule name goes to, well, the value of that expression. So in order for this definition to be fully processed, the expression is reduced down to a value. Function definitions, on the other hand, are already at the outset fully processed. And the rule which they introduce into the language is name applied to, let's say, args. There should be as many as there are parameters. Gets reduced to the expression, body expression, after substitution. So in particular, for example, define square x times x. Here we are. So this definition, Racket looks at it and it's a function definition, so there's nothing to process. Then it'll start processing the next expression or next definition or expression. Well, it's an expression. It's the expression square 7. Now, Racket says, well, square. This looks like a function call because it's enclosed in parentheses. It looks at the first thing within parentheses, and that's square. And it'll try and look up the definition of square, and it'll find the definition. Then square takes a single parameter, and the thing that has been passed to square is already a value. So Racket will take the body of the function, and it'll replace both occurrences of x with 7. And then square 7 gets reduced to, in one step, 7 times 7. Then, on the next step, it'll evaluate 7 times 7 to 49. And that finishes the computation. Whoops. Now, one thing that I alluded to as well was, let's say we don't plug in 7. Let's say we give it 3 and plus 3, 4. Then if I try and run this through the stepper, you'll see that it won't substitute 3 plus 4 into the body of square. Instead, it'll take 3 plus 4, and that expression, it's not a value, and it'll evaluate it. And only when you have values passed to square will it actually expand the definition of square and substitute 7 into the body of the function. So the lesson learned here is that the way that function calls work is that in Lisp, unless you have something that's the definition, when you start by enclosing things in parentheses, it'll assume that that's a function call, unless it's a special piece of syntax like if. Okay, I should specify that. Unless there's another rule that applies, such as a rule that governs it saying that it's definition, or it's a special piece of syntax, Lisp will assume, Racket will assume, that this is a function call. Now, in order for a function call to happen, it has to evaluate each one of its arguments down to a value from left to right. In this case, that evaluation can be done in one step. Then square, the definition will be looked up. You'll look at the body, multiplication of x with x, and you'll perform the substitution of 7 inside that. And then it can compute that to 49. And that finishes the computational trace. Now, another thing that I mentioned before, last class, was that we also have if expressions. And if expressions behave slightly differently from function calls. So here, if I consider, for example, the expression if, and then I nest it, if true, 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 or the two other positions don't have to be numbers. 0 plus 7, 4. And I look at how that steps. So it'll try and evaluate this if expression. Now, the rules that apply to if are if true, if false, and the congruence rule, which directs computation into the first position if the first thing is neither true nor false. So in this case, it directs computation into the first position. That's also an if expression. The first thing is true, so the if true rule applies, and it reduces it just to the thing in the first position, which is true. So in the first step, it'll apply via a combination of the congruence rule and the if true rule, this expression here gets reduced to true. Now notice the expression plus 7, 4 stays there. We're not evaluating it. Whoops. And on the next call, the if true rule applies. And this just gets reduced to 0. And this computation here, 7 plus 4, never gets the chance to run. Any questions about that? Okay, and now I'm going to introduce one more concept today. So I'm not going to talk about structures. I mentioned them last time, but we can do that. I mean, I won't do it before the break. There's one other very, very important concept that I haven't defined yet, and that's lists. So Racket is a Lisp dialect. Well, Racket is a Scheme dialect, and Scheme is a family of Lisp-type languages. But Racket is related to Lisp. Descendant. And Lisp stands for Lisp Processing Language. So the single most important structure in Racket is lists. Now, what is a list? Well, a list can be defined inductively. A list is either empty or something tacked on to a list. Now, if you want to append something to a list, that's called cons for constructs. Cons some expression onto a list. So examples of lists are the empty list, and the empty list, you can either use the word empty, but that's just a name. Empty is not a value. The actual value is this piece of notation. And once you have the empty list, you can form other lists by appending things to that list. So for example, I can cons 2 onto the empty list. Now, Racket provides, we're currently using beginning student with list abbreviations. So the fact that we're doing list abbreviations means that in the way that lists are printed, it'll write them like this. It'll write them as list2. So list is a shorthand constructor. I can say list 1, 2, 3. And this is the same as cons of 1 onto cons of 2 onto cons of 3 onto the empty list. So Racket has an equality test. And I can say, for example, is list 1, 2, 3 equal to this? And it'll say yes. So for nats, you started with Z, and then you took the successor of Z, the successor of the successor of Z. Lists are more expressive. Instead of just forming a successor, list, you append onto your list some piece of information. So it's not just successor, it's cons some expression onto a list. And I'm about to go to paper and I'll show you pictures of this. Now, lists. So now I need to tell you how lists interact with the system of values, but we can also sort of see that. So a shorthand notation, constructing lists, is list. And so, for example, I can do lists 1, 2, 3. This is the same as cons 1, cons 2, cons 3. Any questions? Okay, let me show you some things here.
Just a question.
So going back. Yep.
So why would there then be list and then also the construct? Why do we need both? And then, I mean, we can compare them, but what's the point?
Right. The point is when, so the structure of a list really consists of this information of a list is, okay, so we had nats. How were nats defined? A nat is either Z or the successor of a nats. Well, a list similarly is either the empty list or cons sub-expression onto a list. Now, how do we interact with lists then? Well, if we recognize something as a list, we should be able to tell which one of these two possibilities it is. So because these are two different ways to introduce lists, they have associated predicates, such as empty or cons. Whoops. Empty question mark. Is this empty? It is. Now, on the other hand, I can ask is, let's say, I'll denote it like this, list 1, 2, something formed by cons, and it'll say true. So as a data structure, the way that lists are introduced is as an inductive construction where a list is either empty or cons. Now, the issue with that, or at least the issue with writing every single list is that writing list 1, 2, 3 is much briefer than writing cons 1, cons 2, cons 3 empty list. But when you're working with lists, the way that you'll process them is a structure like this. So this is just a shorthand.
Can the numbering list repeat?
Yes. They don't have to be numbers. So for example, I can form the list of the string hello. And I can have lists inside of lists. So this list should have 3 items. The first item, or rather, if I do it like this, what I've constructed here is, so first off, okay, I'll write it out. So if I write lists, let's say A, B, C, this is the same as cons A of list B, C. This is the same as cons A of cons B of list C. That's the same as cons A. Now here A, B, and C are names, so they don't make sense. But imagine the names being replaced with any sensible value. Oh, right. But yes, the names can repeat.
Okay, that makes sense.
And then just list with no arguments is the empty list.
So is list, when you type list and arguments, are you making a procedure call?
Yes, however, it's slightly confusing when you're dealing with this language because it writes lists like this. Lists, and the other problem is that in this language, all procedure calls have to have at least one argument, whereas, well, no, whereas that breaks here. So the model of the language that I'm giving you breaks if you think of list as a procedure. And the way that it's usually introduced at this stage is, instead of thinking of it as a procedure, just think of it as a shorthand, because the actual list values, which look something like this, are outputted in this form for the sake of brevity. So the answer is it's better to not think of list as a procedure call. Notice that I didn't write an evaluation. I said its equivalence to. Think of list ABC as a value, because if you run it in here, that's the output that you get. So I'm going to say that this thing as an expression is equivalent to this expression. That's confusing. Actually, do you know why it's confusing? Because the language that we're currently working with is beginning student with list abbreviations. I'm skipping ahead one language. It's list abbreviations are something that's added into the second level of teaching languages. In the first level of teaching languages, just with beginning student, you don't have access to the notation list ABC. Okay, any other questions?
Oh, is list 1, 2 equal to list 2, 1?
Well, we can try that. Cool. And it'll give you false.
Also, order is matter.
Yes.
Okay.
So orders and counts matter. But another way that we can describe this is we haven't said what does equals mean in the first place. And we can define equality for of lists in a certain way. Actually, that's a good exercise. I'll do that before we take a break. But let me show you this. So I'm going to run another thing with the stepper. I'm going to say cons, and I'm going to give it a expression, 2 plus 3. onto the empty list. So let's see what the stepper will say. So it's unhappy that this isn't a value. And the first thing that it'll do is it'll actually evaluate this expression. And then notice that in the stepper, I pressed that. It'll replace cons with this. So it looks like the actual list values as the stepper is showing you aren't conses but lists. And that changes with the language with list abbreviations or without list abbreviations. Formally, it's nicer to not think of this as an actual reduction rule, but steppers will do this. But what we learned, though, the important point wasn't that last step. The important point was that in order to evaluate a list, all of the things that you cons onto the list have to be individually evaluated down to values. Let's see what the stepper will do. So I'm just going to type in another expression and then switch over to the stepper again. If I form So it looks, this language makes it look like cons is a function, whereas list is not a function. Although that's misleading to the actual rules. Although you can give the rules in two different ways. So cons 3 onto the empty list, the way that the stepper will show it to you is that that gets converted to list 3, and then cons 4 onto list 3 gets converted to list 4, 3. But I also want to show you what equality is. So, for example, what does it mean for two nats to be equal, where nats are z's and s's? We didn't have equality in our language. Well, we actually, yes, we assumed some properties of equality, but how would you actually test for equality? Well, you'd see whether the number of s's in front of the z is the same. For lists, we can define equality, test equality, let's say. And let's say we take two list arguments, list 1 and list 2. Now, I can write this with if statements. So let's see whether list 1 is empty. Well, if list 1 is empty, then list 1 and list 2 are equal only when list 2 is also empty. Now, on the other hand, we will assume, let's assume either that's L1 and L2 are lists. So in other words, each is either empty or cons something onto a list. Well, if list 1 is not empty, then list 1 is a cons. Now, what we do is list 2 might be empty. So if list 2 is empty, then we should return false. If list 2 is not empty and list 1 is not empty, then both are cons. And lists have a way to access elements. So you can say, if you have a cons, then you can say first. And that'll give you 1. And you can also say rest. And that'll give you lists 2, 3. Because this list is 1 const onto the lists 2, 3. And so the thing that's at the head of the list is the first element of the list. You can also say head. That's another name that's defined in the language. No, it's not. First, then. And then the rest is what has been const onto. And in that case, it'll be list 2, 3. So then you can check for equality of head of list 1 or first of list 1. So in order for them to be equal, if they're both cons, the heads have to be equal and the tails have to be equal. Now the tails are lists, so we can also test equality on the tails. And that's rest. So that was just a very quick definition. What does this definition say? I haven't explained how I'm getting these. 2 lists are equal. So I can define it like this. A cons is never equal to an empty list. And 2 cons lists are equal if and only if their heads are equal and their tails are equal. Well, I will call them heads and tails. The head of the list and the tail of the list is the rest. And in this equality test, in general, these are lists. Now, the heads might also be lists, so I'm sort of cheating by running equal here. But if we assume that, for example, these were lists of numbers, there's a version of equality that only applies to numbers, equals 1, 2. But if you try and run equals on, for example, Booleans, then you get an error. So this is a function. Let's replace equal with equal that defines, checks whether 2 lists of numbers are equal. And so it'll say false. And we can look at how this behaves with respect to the stepper. So here I want to test equality under these two lists. Now, the definition that I gave here, it's complicated. So I got a bit sidetracked in giving this. But it goes into this expression. It looks at all occurrences of L1 and L2, which there are many, and it replaces them in the body of this, all occurrences of L1 and L2 in the body of this expression with the provided values. Then this expression is an if expression. It asks, is this list empty? Well, it's not. And so by the if false clause, what I really want to do, I know that the first list isn't empty. Now, in order to compare them, I check whether the next list is empty, and that is false as well. So in this case, both of the lists are cons. They're not empty lists. Both are something cons onto something. And then in order to test for equality, what I do is I take the first element of this list, and I'm assuming it's a list of numbers, and the first element of the second list. Now, those are calls, procedure calls as well. So first of this list becomes, well, 1. First of that list becomes 1. I check for equality. It's true. And then I check whether the second condition holds. In other words, whether when I test for equality for the remainder of the lists, it holds. Now, rest of a list isn't a value, so those also get reduced to list 2.3 and list 2.4. And then I repeat this process. And once again, after going through it again checks whether the first elements of these two lists are equal. In this case, it's a 2. In this case, it's a 2. So that goes through. And I look at the rest of the lists, and I make the call again. Then the same thing happens. They're not empty. And now I try and see whether 3 and 4 are equal. Then I get false. The AND statement fails. And the AND statements fail up to the top. And I finally end with false. So I didn't expect you to understand that, because I've just introduced all of these definitions. But that's what the computational trace of something like this would look like.
Question.
Yep.
So, well, why wouldn't, I guess it's not defined, but is there any advantage to just using something like this over like a for loop?
Oh, there are no loops in beginning student. There is no loop construct.
So, okay, follow-up question then. Can you define a loop like recursively?
You asked me that question because you thought one was similar to the other, right?
Uh-huh.
Well, if you see the similarity of this recursive process to how you'd write it with a loop, well, that sort of answers your question as well.
Oh, okay. No, the reason I ask it is that like this is it's cool, but I'm just wondering if there's like any is why would you like do things like this instead of just writing for loops?
Oh, well, for one, we can understand this language. We have a model of how this language behaves. I can explain the language in terms of rules, purely as a formal system. And the second way is that writing code like this is actually much safer, in that it's much harder to make an error if you follow proper principles of how to design the code. Also, at the moment, this language isn't very much a functional language. It's a functional language in that it doesn't let you rewrite variable names, and it has functions, but it isn't exploiting what will come next. Eventually, by the end of the week, we'll see that functions can be passed as parameters into functions, and functions can be returned, and that functions are values as well, although this isn't true in this language. And working in an imperative language, in other words, a language where you can rewrite variable names and where you have for loops as you're used to, it's much harder to have what is called first-class functions in such a language. So this language, the power that you'll have by passing functions and returning functions outweighs the benefits that you'd have in imperative languages. And yes, imperative languages also let you do that, but not as efficiently, and this language forces your hand into writing things in a certain elegant way.
Yeah, so last question, because I was just like looking at like, it's very rare that something like this I find manages to take 500 MB of RAM.
Oh,
and I'm just wondering
Dr.
how
Racket
it's managing
is
that.
consuming its, it's the actual graphic application that's using most of it. It is not taking 500 megabytes to run this. For example, when you submit your code and it's run on command line, the memory limit is 30 megabytes.
Okay, that's better.
And that limit is hard to exceed.
Okay, that's good.
So if 500 megabytes is the total system memory that Dr. Racket is using at this moment, you see that at the bottom. Lisp is slightly less memory efficient than other languages, actually not slightly less, but it's not as terrible as you'd think, given that 500 megabytes of RAM indicator.
Those are like electron numbers. I was like, huh?
Yes. Now, also, you'll notice that the expressions here become larger. And you have sort of, if this were very long and recursive, the program itself would get longer, the expression. You'd have things bubbling up outside of recursive calls. There's a way to deal with that. That doesn't have to happen if you write it differently. So there is a way to write efficient code. This isn't necessarily a good example of what it. Okay, does that answer your question?
Yes.
Okay, let's take a break, and then I'll switch over to paper. So yes, let's resume at 3. Sorry, I'm a bit tired today, so that was less organized than I would have hoped. Oh, also, if you look at this memory amount, you can ask Dr. Racket to clean up the system memory that it's using by pressing this, and then it'll go down a bit. So that's it. So the 500 megabytes are just required for having this up and running. But also, both programs are currently running. All of these definitions are currently standing, and the REPLs are still active. Okay. Okay. Let's. Okay, actually, there's one more thing that I want to define here. Let's, for example, define a function that takes a list of numbers. And returns the sum of all of the numbers in the list. And so first off, what will this function definition look like? So how do I start a function definition?
With the word define.
Okay, let's call it SumList. Then
A parameter?
what? Sure. How many parameters do I want?
I guess just one.
Yes. And what should the definition be? So first off, how do I interact with a list? There are really two ways that I can interact with a list. An empty list, well, I have predicates. But predicates aren't really much of a way of interacting with a list as they are of classifying things. Predicates empty or cons. Now, empty lists, well, I can construct new lists from empty lists. Now, I want this to be a list of numbers. So I can construct new things by cons number. List. But if I want to take lists apart, then if a list is a cons, then I can say first list and rest list. And first list is a number if list is a list of numbers, and rest list is a list of numbers. And I can also write if statements. So those are my ingredients. And now I'd like to write this SumList function. So what do I do?
Take the first of the list and add it to the sum of the rest of the list?
Sure. So let's, oh, I also have, I guess, plus. So I'll take the first of the list and I'll add it to the sum list of the rest of the list. So let's run this definition on list 1, 2, 3. And I'll put it through the stepper. Before I put it through the stepper, let's also comment off the definition above so that it doesn't cloud up the screen. So we'd like to find the sum of the elements in the list 1, 2, 3. Now, I look at the definition, and list 1, 2, 3 is a value. So it looks up the definition of some list. It places that list in for all occurrences of list in the function body. And so I have the sum of the first of list 1, 2, 3 with some list of the rest of 1, 2, 3. Now, what happens next is, what will the next step be after this?
It will evaluate first list 1, 2, 3.
And what will it give?
It will give 1.
Good. And what will it do after that?
They will do the sum list of rest of list 1, 2, 3.
So will it call it, or will it do something else?
It will be called again, I think.
Let's see. So first list 1, 2, 3 gets replaced with 1, as you correctly predicted. And now you're saying that it's going to go to some list and substitute in its body this?
Yeah.
Well, that's can be evaluated. So before making a function call, that has to be a value. And rest list 1, 2, 3 is not a value. List 2, 3, on the other hand, is a value, right?
Yeah.
So now it makes the call. Sum list 2, 3. Once again, the same thing happens. The first becomes the first element of the list. The rest becomes the rest of the list. And then it makes the call sum list 3. Now, the first of the list 3 becomes 3. The rest of the list 3 becomes empty. And the call is made again. And then it tries to take the first element of the empty list. And what happens next? Well, we haven't seen this yet. Can anyone predict?
Well,
Does
the
this
empty
language
list.
have a null?
It will throw an error. First, expected an argument of type non-empty list given empty list. So what happened there was that, so this function works by stripping the first element of a list off repeatedly and then summing the rest of the list. Well, the rest of the list eventually gets down to the empty list. And then when you try and sum list the empty list, it'll try and take the first element of that list. But there isn't a first element. That list has nothing. And that's where it throws this error, saying that first expected a non-empty list, but it was given the empty list. So we should fix the definition.
Can we define the sum of an empty list to be 0?
Oh, geez.
How? Okay. Yeah. Yes, we can. How would we do that? Oh, you still need to make a single definition.
We can use
Go ahead.
if statement.
Sure.
If
So what
Can't
do
you
we
just
check?
put an if in the first list thing, like inside first list? You just check every
Here?
time. But I guess that's inefficient, right?
But a global if would be better. I mean, when you, actually, okay, no. We can.
Is that better or worse?
Let's do your suggestion after we do this one.
Okay.
I think there's an interesting point to be made about your suggestion as well. Okay, so let's say we want to start it with an if. What would the clause be?
Empty
If.
question mark list.
And if the list is empty, what is the sum of the elements in the empty list?
0.
Good. And otherwise, it's a cons. So does this make sense for a cons?
Looks good.
What we had before. So I'll indent it like this. It'll check whether the list is empty. If the list is empty, it'll give 0. And otherwise, it'll take the first element of the list and add it to the sum list of the rest of the list. And for brevity, let's just make it sum the list with 1, 2. So we try and sum list 1, 2. List 1, 2 is a value. And so it'll go look up the definition of sum list, look at its body, look at all occurrences of list, which is the parameter of the function, and replace them with the operands. Then once again, it'll be, well, now it's an if expression. And in an if expression, what's the first thing that happens? What are the rules governing if expressions? So what's the first thing that we need to do? Well, putting it another way, what's the next step of computation that happens?
We need to evaluate the conditional expression, the first one.
Right. And so that's empty list 1, 2, and what do I get?
False, or hashtag
Yep.
false.
Hash false. There we are. Now, so now I have if false 0 something. What do I get?
The second thing.
Yes, by the if false rule. So it reduces to the second thing. Now, the second thing is sum something with something else. What happens next?
The first thing that is being added needs to be evaluated. In other words, first list 1, 2 gets evaluated.
And what does that give?
1.
Good. Next. Well, what next?
It will be the rest list 1, 2, which is 2.
Is it just 2?
It's just 2, I think.
So you're saying that all of this will be replaced with the number 2.
List 2.
Good. Then that's a value. And so it's allowed to proceed. It'll expand the body again. And notice now I have +1 and this body. And originally it was just some list. Well, actually, let's look at yes, let's look at this call right here. We started off with some list 1, 2. And then after a few steps, it got reduced to +1, some list 2. Then the same thing will happen. First, the empty condition gets checked. It's false. So instead of going with 0, we're going to go with the second body expression where we actually access the first of the list. That's 2. Then I make a call. The rest of the list is empty. And then I try and compute some list of the empty list. Now what happens?
That expression will be hashtag true, 0, then.
Yep.
Yeah. And then there'll be 0.
Yes.
The entire if statement. Yeah. +0. Then. Yeah. Yeah.
Oh, also, when I was saying hashtag, that was partially a joke. It is the symbol is called hash.
Okay.
You tag people using a hash. So I do not want to be the person who is responsible for people always saying hashtag instead of hash.
Okay.
Okay, let's call it a hash. Yep. And then the arithmetic expression gets evaluated. And then that just gets down to 3. So the original list was list 1, 2, and some list 1, 2 was 3. Oh, now can we, I think there was a suggestion of a different way to write it.
Yeah.
So what did you want to do?
Put the conditional inside like the thing which has first right now. So you'd have if empty and then evaluates to true, then first LST, false, then
Otherwise.
0.
Sure. Can you see what's going to happen now? Do you see?
I mean, I think it should be the same. No, I was just, I'm
Sure.
not sure.
Let's try sum list 1. Let's just try and run it, not step through it. That is because there is some. Because there are 2 definitions of sum list, of course. Sum list 2. And if empty list, okay, 0. Okay, let's try it like this. And then what do we get? We get rest, expects a non-empty list given the empty list.
Oh,
So you've applied the condition on the, so if you have, there are 2 things that fail. If you try and take the first element of an empty list, it fails. And if you try and take the rest of an empty list, it also fails. So both of these calls, first list and rest list, will cause an error if you actually evaluate them on the empty list. So you have to protect both against that.
I see. I see.
But then you have an
Wait,
if condition here and an if condition here.
Okay.
And then you may as well bring them out front.
Okay, I see.
Now, there's another issue that you pointed out before, and I guess that's a memory issue. What if it's a very big list? Like I can produce very big lists. I can define functions that'll make me. Who wants to? Let's say I want a list with lots of elements. What's a quick way to build a list with lots of elements? Does anyone have a suggestion?
Just keep counting up natural numbers.
So I mean, I want to do it with some functions. So give me a function definition.
X squared.
I mean, what should I define? I want some function to let me produce a big list, meaning with lots of elements, not with big elements.
You probably want to apply cons several times. So
just a successor, like just cons.
Yeah.
Oh, well, okay. So I can, let's say I'm going to call my function f. So what's it going to take? How many parameters?
Oh, well, are we allowed to do like for I in 1 to
Nope.
n loops? Okay.
No such construct.
Okay.
Takes in a list, right? And gives you back a list.
Sure. And what list is that?
Oh, well, I mean, the cons.
Cons what?
LST.
Onto? You know
empty.
what? Let's make these be lists of numbers. Oh, actually, so let's see what this function will do. So if we look at this function, cons list onto an empty list. That function, if we pass it any lists,
I'll just give the list.
The identity, right?
will it?
Well, the cons, yeah, it should be the same thing, would it not?
Yeah.
Let's see. So can anyone
Oh.
explain what happened?
Oh, yeah. When you say cons whatever, you put the whatever into
Oh.
the element of the list you're making. So since you had list as a whatever, you have a list inside a list.
Right, because for example, if you take cons whatever, let's say 12, whatever, this is going to construct a list. The empty list is a list, and this is anything. So this is a list. And if you take the first of a list, it'll be whatever, right?
Yeah.
So here, what you're doing is you're constructing a list so that if you take the first of it, you'll get list 1, 2. But it itself is a list whose first element is list 1, 2.
Oh, I see. So I guess you have to flip the order of like LST and the empty list.
Okay, so cons empty list onto LST. So if I do, well, let's say F of the empty list, then it's a list whose head is this and its tail is it's cons empty. So list, this is the same as cons
Oh, I see. Okay.
empty list onto empty list.
Like the thing is, I don't see how you can do that. Like, make this work without assuming it's a number. Then, because like you have to like do something. I mean, you could do cons
Well, you
one
can add a
list.
second parameter.
Oh, the first element of the list, I guess, or something like that. I don't know.
Oh, well, I
And then
mean,
you can just get a big
let's
list.
make it a list of numbers. Let's say we add 0 onto the list, F list, right?
Uh-huh.
So doing that, if we go F with the empty list, we'll get list 1, list 0. And then if we apply F twice, what will we get?
0,
0, 0.
0.
Yep. But now what's a quick way to make build this quickly? So I could type F over and over again and I'd slowly build up a list, but that's not an efficient way. We'd like to make lists very, very big, very quickly, using a minimum number
Oh,
of
take a second
keystrokes.
parameter.
Sure.
Hmm.
What type of parameter is it going to be?
A number?
Yeah.
Sure.
Like
Now what? So let's suppose that number is a natural number.
Yeah.
So
a
you do
natural-
it again, and then recall it with n-1.
So what do I do? What is the body of my function?
F. And then like the list would be cons 0 LST, I guess. And no. Would it?
Well, that's fine. And then what's the second argument?
And then n-1. So minus n1.
Sure. You can also write in sub 1 n.
Oh, cool.
So let's try and run this. Oh,
Well, we
the
need a
memory
base case,
usage
don't
notice
we?
right now before I did anything is a gigabyte, because so sometimes this is you press this and then it goes down to 514. Okay, so it's cleaned up. But remember how I had very low memory usage? Those were the good old days. So let's just see what happens if I do F onto the empty list n0. Oh,
you forgot to run it. You just typed it in.
yep. Thanks. So what's going to happen?
We're gonna get a really, really big list.
That's one way to put it. I'm also going to get no lists and the memory. Look at the memory usage. So it's
Gosh.
800.
Yeah.
Okay, and then it says increase memory limits to. Oh, so right now, notice the memory limit, it says 128 megabytes. So while Dr. Racket is using lots of memory, the memory limit of this application is 128 megabytes. And however much time that's took, it's got to 128 megabytes. So increased memory limits to 256 megabytes, let's say. Okay, nonetheless, it ran out of memory. Why? Because it never stops. It subtracts 1. You subtract 1 from 0, you get -1. Then you get -2. And then you get -3, and then it just keeps consing on.
Maybe. How about you then just add if equal question mark.
There's, by the way, a
someone.
0.
Yeah.
There's
0.
also, you can test 0n. Then what?
Then we just fcons 0 LST. I mean, no.
So that's what happens if it's 0.
Yeah. I guess just cons 0 LST.
Sure. And otherwise, what? Well, the call, we continue making the call, right?
Yeah.
So that
So
will
then
make
I
the
can-
length of our list n+1, right?
Yes, it will. So then if I do F0, I'll get, F empty list 0. It'll give me list 0. Now, if I wanted to make the length of my list n, instead of returning con 0 list, I could return just list.
How about, or it could make it 0 question mark n minus, or like sub 1 n, right?
Yes. Yes, that would be another way to fix it. If you wanted to do it, no, that would fail if you put 0. Then, if n is 0, then you'd get -1, and it would get into the same error as before.
Okay.
But
Is there,
whichever, go ahead.
is there a way to see if it's like a type of number, like a positive number, like positive question mark, or do we have to define
There
it
is
as
greater than.
Yeah, because this
and
breaks
0.
if you have a negative number.
Yeah.
Like if you
Or
pass in
greater
a negative
than
number.
equal
Then
to.
it's-
Yeah.
let's see
Okay,
this.
that's a good point. So we can do that. If you want to be safe in that way, which is a good thing to do. So if it's less than or equal to, then it fails. So if n is less than or equal to 0, then we're done, right?
Yeah.
And by the way, let's not make it so boring. Instead of
Okay.
consing on 0, we have some number. Let's cons on n.
Okay.
Okay, so if I do f of 0, f of the empty list and 0, what do I get?
You just get the empty list.
Good. And then if I put in 10 here, what do I get?
Like a lot of empty lists.
Well, what's the first element of the list going to be?
Yeah,
10.
let's go.
Anyone
One.
else? Okay, why?
Because f cons n list that n is 10.
Cons add stuff to the, like, you know, it like pushes, right? Like at the end. So like you get stuff in the start when you like add things with cons.
So for example, what's the first element? What's the first call that happens? The first call that happens is it conses 10 onto the empty list, right? So the empty list is the back, and then onto the back you cons 10, then 9, then 8, then 7, then 6, then 5. And then the last thing that you cons on is 1. So for example, cons 11 or onto this, 10 is at the back of the list, not at the front. and you add something at the front of a list. So the first of the list of this list is going to be 1. Okay, so that's a quick way for building lists. Now that we have this way of building lists, we can put that into SUMList, and we can step SUMList f empty list. And so now this would sum the numbers 1 through 10, right? If I put f list 10. Now let's run this through the stepper. So the first thing that it's going to do is it's going to compute f of 10. And I can skip a few steps by going to the next call. So it keeps building it. So it's added 10, 9, 8, 7, 6, 5, 4. Then it's doing this next call. Okay, so finally it's computed the list. It's list 1 through 10. And what I'm trying to do is now I'm trying to SUMList this list. So look at the box on the left. So SUMList is going to reduce in one step to, after several steps, what's the next nice? Okay, well, that's not a nice way to put it, but skipping a few steps, I eventually get down to here, +1 SUMList. I've taken the front thing, I've put it out front, and then I'm SUMListing the rest of the list. So this is skipping a bunch of steps. This is before the next procedure call. And then notice how it's building this up, and it keeps getting bigger, right? And so this expression that's here, it keeps growing. Well, the list keeps shrinking, but this expression keeps growing. I guess overall, the memory usage is staying roughly constant. But we could also define a version of SUMList that didn't have this problem. So can we define a version of SUMList that does not have all of these pluses accumulating at the front? So for example, if I just take the first element of the list, let's say I ask you to sum the numbers in this list, just colloquially, how would you do it? Not in programming.
And then 10 plus 1 divided by 2.
So you start with what? So describe what you do.
We add the first term and the last term times the number of terms in the list.
Okay, fine.
2.
Fine. Yes. Yes. So you can predict ahead of time what this is going to be. 1 plus 10 and 2 plus 9 and 3 plus 8 and 4 plus 7 and 5 plus 6 are the same. So I think Gauss as a child figured out a way to sum the numbers 1 through 100 using this.
Yeah.
And what did he find? So there are going to be 50 pairs, and the sum of 1 and 100 is 101. So what is 50 times 101?
50, 50.
50.
Yep. So for example, if we say SUMList f 100, we should expect the same results as we do. Okay, but let's suppose that the numbers in the list are completely random and you're summing them. How would you do it?
Oh, add the first one to the second one, write down the result, then take the second one, and then go from there.
Add it to your previous result, right? And then,
Yeah.
so you'd keep a tally. You'd keep a running tally, right?
Oh, reduce. Oh,
But right now, this function SUMList isn't doing that. This function SUMList is pulling out all of the pluses and only doing the computation at the end. So if we looked at how it's stepped, I'm going to go to the stepper again. What am I calling there? I'm calling there that. Okay. So back to the stepper. So if we try to SUMList this, well, first off, it would actually build that list. So it's building that list. Then it's SUMListing. Then it's pulling out each one of these out front. So look at the box on the left. So actually, let's go back to the start. So how this happens, the first step of the computation is building this. Well, that's the first phase of computation. So it tacks on 10 to the empty list and it reduces 10 by 1. Now it's built. Now it's actually going to start SUMListing this. And what SUMList does is it takes the first one off, it adds it as a plus to the rest of SUMList. So it's taking the 3 out and putting the plus 3 out front. Then a 4 out, then the 5 out, then the 6 out, then the 7 out, then the 8 out, then the 9 out, then the 10 out. Then SUMList of the empty list is 0. Oh. Okay, now I press next. And now finally we get down to this expression, and then it starts evaluating it. So it goes back out front and computes the value, 55. Okay, so how do I do it if I want to keep a running tally?
Define a variable.
Sure. So let's call this define SUMList 2, and let's keep a tally. I'm going to call the tally accumulator. Now, how does the function definition change? Well, I mean, so it's also going to, let's say it starts with this. So if the list is empty, what do I return?
The accumulator.
Good. And otherwise, well, what's this call? What does this call get replaced with?
Plus first list and accumulator.
Well, accumulator is just a number, right? So that would take the first elements of the list and add it to the accumulator, right? And then what? That's it?
And then call the function again, but with the rest
on
of
what?
the list. On the rest of the list and the new on this expression that we just wrote.
So you want the top thing to be a recursive call, SUMList.
Yes.
Then what is the first parameter? What do I feed it for the list?
Rest list.
Good. Then I take the first element of the list and I add it to our running tally. That matches up with the intuition we had before. We have a tally, we add it to the tally, And then if there's nothing to add, we just give the tally back, right? So that's sum list 2. Now you'd have to call that with 0. So then we could define another version of sum list. Let's say 3 that only took a list. And all that it did is call sum list 2 on that list. And 0. Then I can call sum list, let's say 3, and my build function that lets me build things up. So that should give us 50-50. I meant to say sum list 3. And if we looked at the trace of this function, let's make it run this.
Question.
Yep.
Is there a profiler you can use so we can see like the actual time differences for like the different versions?
There are built-in Racket versions. So yes, full Racket has a profiler. I'm not sure whether the teaching languages have that enabled. There's also a time function. I'm not sure if it's available for beginning students. If you increase the language sophistication, then yes. Yes. I can't do it now, though. I don't think it's available in this version of the language directly. Okay, so in this case, I build the list. Oh, you can also do it off command line. You can call Racket's script off command line. And then use system timing things. But Dr. Racket has a built-in one as well. Or you can install it as an extension if it doesn't. Okay, so now sum list 3 calls sum list 2, and now there's an accumulator. And now if I look at every next call, it's going to add those numbers to the accumulator instead of keeping them out front, right? 55, and then it eventually gets to here. So, okay, those are 2 definitions that I wanted to show you. Let me just write a few things on paper, and I'll end in 10 minutes. But I want to show you a few things first on paper. So ignoring, let's imagine that, let's ignore the list notation. For now. And in this case, a list, or writing it like this, a list is either the empty list or its cons of anything, any expression, or let's say any value. Onto a list. Actually, let's call this, well, a list value. No. Like this. In which case, if we were to look at these as ASTs, for example, consing 1 onto cons 2 onto the empty list, looks like cons let me draw it in blue. One onto cons 2 onto the empty list. And then if we looked at SumList and we ignored the fact that there were ifs inside of it, at a higher level, after the ifs, SumList could be defined as by these following two rules. So suppose I have SumList of the empty list, or I have SumList of cons something onto something else. So the actual definition of SumList involved checking which one of these two cases it was. But if we combine those multiple steps into one, what would the reductions be? So if I do SumList of the empty list, what do I get?
0.
And if I take SumList of a cons, what do I get?
You get plus V SumList L.
Yes. So we can think of our definitions as, well, there were a few more steps involved in the ifs checking which case it was, but if we ignored that, then our implementation was really an implementation of these two rules. SumList of the empty list is 0, and SumList of any cons replaces that with a plus of the head of the list with SumList of the tail, the rest of the list. And then if we looked at our original tree, well, or if we looked at this tree here, or rather, let's say we look at SumList cons 1, cons 2, cons 3, cons the empty list. So with one application of these rules, what happens?
It'll be plus 1 cons
The
2
SumList.
cons 3 cons the empty list.
Plus 1 to SumList. Oh, okay, I will fix the color in a second. Cons 2, cons 3 onto the empty list. And then if we applied several more steps, so skipping a few steps, eventually, after all of the sum lists have gone through, I would have plus 1, plus 2, plus 3, 0. So if we look at the shape of what this does, some lists started off with this cons expression here. Then when it encountered a cons, it replaced the cons with a plus and then applied some lists to the list that was the rest of the original thing that it fed to. And as some list gets pushed down this tree, eventually it's pushed down to the empty list, at which point it becomes 0. So some list applied to this tree right here, eventually after several steps, brings it down to this AST here. Here we are. So all of the cons have been replaced with pluses, and the empty list has been replaced with 0. And then eventually that begins to compute. And then eventually after several steps of computation, it's just brought down to a single value, which in this case would be what? What's the value of that expression?
6.
Good. So we wrote a program to sum a list, and if we ignored all of the steps that's checked which one of these two cases it was, then we could write rules like this. Sum list of the empty list goes to 0. Sum list of a cons goes to the sum of cons with sum list applied to the rest of the list. And then if we apply it to any list, what does any list look like? Any list is either the empty list or cons of something onto the empty list. And if it's a list of numbers, then we're going to insist the thing that we cons on is a number. And then it just goes through, and that's the picture of the program. Any questions? So I'll end with that for today. The first hour was much less organized than I had intended. But so last time we did a very quick whirlwinds tour of Racket, and now I've explained some of the features in greater detail, but I haven't still given you formal definitions. And there's homework that I'd like you to finish by tomorrow midnight. It requires you to just write out 2 computational traces, then rewrite 1 arithmetic expression in prefix notation, and rewrite 1 list that's written in list form as a list that uses cons in cons notation. Any questions? Okay.
Will you send us an email detailing all the requirements for homework?
Yes. The homework is being uploaded to the homework page, which I sent to you, but I'll resend it again. And I'll send, so I should have both of these links on the course homepage. I should put them up. I haven't yet. I will send links to the submit server and to the homework page and to the notes to everyone once again.
Okay, so will the notes be updated with this, or?
The notes will not have the definition of cons and lists. So you'll have to use the lecture for the definition of cons and lists.
Okay.
I mean, I'll see if I can write something, but I'm sort of skipping ahead to the third chapter here. The second chapter was supposed to be a lot of details about computational rules, which would make more sense if we had done more we had done any set theory in the first week. But we didn't. But okay, I'll start producing notes about this section as well. So if you need some definition for the homework, send me an email if something's unclear and I can point you in the right direction, or I can write something up then. And I'll send everyone a link to the homework page again immediately after. Anything else? Okay, see you tomorrow.
See you.
See you.
Yeah.
Thank you.